Hey, thanks for coming back and watching my videos up until now. I haven't made many and they weren't what I expected to make. It's been a longer journey than I thought it would be. To be honest, I haven't produced the variety of content I expected, and I really didn't think I would still be using this setup. So let's fix that. First things first, I wanted full body tracking. Last time I got it functional, this time I'd like to improve it. Running on the CPU turns the necessary calculations into a critical path, or bottleneck, for my software's main loop. So it's time to move it to the GPU, and learn how to move things to the GPU. GPUs have a ton of little processors that all execute an instance of some small task simultaneously, so they're great for performing the same calculation on a whole slew of different data points, like vertex positions. That said, I have to feed all these kernels input data ahead of time. Input data that currently exists in the CPU and only the CPU. The tracking actually needs a lot of reference data, especially for the blend shapes. My system originally performed 3 stages sequentially since it's currently single-threaded. The anim vertices are distorted by the blend shapes, then the pose is updated using body tracking data, before the anim vertices are moved to their final position. I want to move most of these calculations into the GPU, where they are performed on each vertex. The pose deform will still be done CPU side, because each bone position depends on its parent position, data that is external to the vertex kernel's context. The actual vertex translations, both blend shape deforms and final pose translations, will occur in the GPU, which means the GPU needs all the data necessary for these translations before it can execute. That means my tracked pose and blend shape data has to be passed in as a buffer object, in addition to the target position every vertex occupies in every blend shape. Remember that a blend shape is a 3-vector linear interpolation applied to each vertex of a mesh between the base mesh data and another blend shape mesh data for each blend shape. On top of that, blend shapes themselves are linear combinations of underlying shape keys. To give the GPU what it needs, I need to pre-calculate all the final blend shape data, shove that into a big buffer, and place it into a global buffer so all the little engines can access it. Since this ended up being pretty large, I used an SSBO, a shader storage buffer object. This was rather large. Now, each engine doesn't actually know what vertex it's operating on. There is some kind of GL vertex ID input, and I don't think that actually means anything to me. So I had to calculate the index into that blend shape data buffer for each vertex and then put them into another vertex buffer. This way the vertex knows what data to pull. So my vertex shader has the standard inputs: vertex position, texture, coordinate, normal, color, the camera stuff, MVP, model view, normal, matrices, as well as my custom buffer objects: vertex SSBO index, bone associations, bone weights, mesh offset, blend shape position SSBOs, blend shape normal SSBOs, the tracked blend shape uniform buffer, base pose transforms UBO, and the tracked pose transforms UBO. As a side note, I had to add my own implementation of uniform buffer objects to Raylib. It was super easy since I compiled the library myself in the first place. Raylib is great. There wasn't much to do after setting up the buffers on the GPU. It was mostly transferring the algorithm from my C function into the vertex shader. That said, none of my meshes have their texture. This turned out to be simple. I was accidentally overwriting my texture coordinate data in the GPU with textcord2 data instead of the textcord1 data. With everything in the GPU, performance is quite a bit better. I can go back to using 60 FPS, which is a 100% improvement. That is definitely a huge performance improvement and certainly not merely returning to my initial target performance. I did want to smooth out this jittering a bit, essentially a denoising function. You're probably familiar with noise on some kind of signal like audio. It's all these random deviations from the true signal. But what does this actually mean? A signal is the measure of some magnitude at many points in time. While we usually talk about the amplitude of some signal, auditory or electrical, this graph could represent any magnitude. Speed, altitude, water level, distance, x position, y position, z position. You can take any higher dimensional vector and break it down into base single dimension magnitudes and generate this graph from each, a process I performed on my body tracking data. Working in a single dimension simplifies things and allows me to use almost any denoising technique I want. I went with two basic examples. The first is thresholding. This is pretty simple. You specify some outer bounds for the magnitude you are measuring and ignore any measurement outside those bounds. This usually is some physical value or a multiplier on whatever is expected. I decided to go a step further and scale off the position extrapolated from two other measurements. My system caches 5 measurements total, 2 before and 2 after the currently rendered frame. This lets me extrapolate from both directions and select the thresholding window. It may add a 2-frame lag to the body tracking, but that's the least of my concerns. The second algorithm I implemented is a Gaussian average. This is pretty simple. Generate a normalized Gaussian curve, then use the sampled values as the weights in a weighted average. The matrix with the weights is an m by n discrete Gaussian kernel and is pretty straightforward to implement. While thresholding removes sudden jumps and outliers, the Gaussian kernel smooths out jitters in the motion. I programmed a 5-sample and a 3-sample kernel, but 3 seems to work fine. Finally, I want to tweak the look a little bit. My model looks quite nice in VC face, but doesn't look great with the default shader. I'm playing around with my shaders, and it's horrible. Cow, it's ugly. So now it's time to play with the fragment shader, which is actually quite nifty. The vertex shader places the vertices where they belong. The fragment shader determines what color each pixel should be. I had to go back and fix the normals, which I skipped over earlier, but are also going into the GPU. After that, I added some basic lighting and this little edge outlining effect. I think it's neat. I built some hand tracking gloves, loosely based off of Lucas VRTech's Lucid gloves, because I thought the potentiometer flex system was clever. I didn't need haptics, so I ignored that stuff and doubled up on the flex sensors to increase fidelity. When you stop and look at it, human hands have incredible mobility. The base and middle joints of each finger can be moved separately, and in addition to flexion, extension, you have adduction and abduction for each finger. You even have a tiny bit of circumduction. Needless to say, I'm not capturing all of that. I've captured flexion and extension. I may be able to implement some kind of adduction and abduction system if I decide to go forward with upgrading these gloves. I didn't get as far as I would have liked with them. I wrote my own firmware. The end system became rather complicated, and I ended up using 2 microcontrollers per hand, an Arduino Mega for the actual finger measurements and an ESP32 for wireless communications. Thankfully, integrating the system into my software was straightforward. The most difficult part was applying the rotations to the model's armature. If I was going to recommend something for the Lucid VR build, I would stick with the 3-wire ribbon cables he recommends and standard connectors on both the potentiometer side and the microcontroller side. Don't daisy chain. Design a circuit board. This will work well with the ribbon cables, keeping everything nice and clean. And if you pay someone to fabricate your board for you, you can go 4 layers, a low voltage plane, ground plane, high voltage plane, some kind of connection plane. This should help isolate from niche electromagnetic effects. No, you shouldn't really have any of those. I would add some kind of LiPo battery and LiPo battery controller, though the cheap Chinese ones make me a bit nervous. This would let you avoid that bulky battery pack. I'm not much of an expert, though, so I decided to fix a few things on my model. My skinny noodle fingers, lack of tracking on my collar, weird mesh gaps. This caused some unexpected issues while exporting my model to VRM when the bones were suddenly just wrong for no reason. That took a week to fix. I also had to spend some time adding in the wrist rotations from the body tracking, which is still a little finicky, but at least my hand doesn't crumple into my forearm. And now I have a working setup. Mostly. Hello. Welcome to my channel. I decided to build my own tech stack to differentiate myself, and it finally feels like I'm standing at the starting line. Just the starting line. There's still a lot of work to do. Some things to fix, others to upgrade. This should be good enough for a beginning. Hopefully you'll see an improvement in production value. I've also felt pigeonholed. I fell back on my computer educational-ish videos since that's what I'm comfortable with. That was never my intention. In the future, there will be much more variety. I'd like to pursue anything that catches my interest. There are so many things that seem fun to make, it's a bit overwhelming. Though at the moment, it feels a bit empty, doesn't it? For now, we should take our first steps.